missing this. Now, let's look at this. How do we implement superconducting qubit? Sorry, a spin qubit. Again, 5 criteria. So we will try to look at how we have a scalable system. I think, right? How with the well-characterized qubit, 2 levels, how to initialize it, and we need a long decoherence time here. We don't discuss it much. A universal set of quantum gates, and we should be able to do measurement. You can ignore this. This is for quantum communication. Right, these 5 criteria, another hint. So let's start. We can use silicon qubit. Why it is good, right? Because error correction is required to protect the qubit. You see that so far it's like analog computing. You rotate a qubit. If your initial phase has problem, you cannot make sure that you have 100% correct phase, right, in any electronics. Your magnetic field might not be 100% accurate as what you want to put, right? And then the time, look at this, Hamiltonian. The time will determine the gate. The time won't be 100% accurate, right? So then you won't be able to do the gates without error. And the error will keep accumulating when you apply more and more gate. Then it will fail. So quantum error correction is a must. But how do you do quantum error correction? You need about 100 to 1,000 physical qubit. Let's say many spin qubit. You make entanglement, and then you have some very sophisticated correction algorithm. Then you can protect it from noise if they have low enough noise from the beginning. Now then, that is almost impossible. For example, Shor's algorithm, people say you need about 1,000 working qubit to be useful. And then it means you need maybe 100,000 to 1 million physical qubit in order to make a useful superconductor, quantum computer. Then, what in this world can achieve this type of integration? IC chip, right? No, nothing else can do that. We can put billion. So definitely you think that maybe silicon qubit will be good. Ideally, you put a qubit here, and then you have the control electronic very close to it. But this need to put in low temperature. Let's see. We will see that very soon on the low temperature. But silicon qubit from the integration perspective, only integration perspective, they are very promising. But they have many problems, of course. Right? You can use spin in the new electron or spin in the nucleus as the qubit. But here we talk about the spin in electron. So how do we have the first criteria, right? Scalable. Yes, looks like it's scalable if I can put on a silicon chip, definitely. Do I have a well-characterized qubit state? Now, first of all, we are going to use silicon as the substrate, but silicon has isotopes. Silicon 28 is the most abundant, but still maybe 28 plus 30 is only 95%. And then you have 5% of the atom. Every 100 atom, you have 5 atoms, which is silicon 29. 29 means what? The mass number, right? The number of neutron plus the number of proton. Now you have odd number, it means you have spin, because neutron and proton have spin also, a spin half. Then if you have spin in the nucleus and you're trying to do quantum computation using electron, spin will interact with each other because both of them has spin magnetic moment, right? They generate a magnetic field and they will just interact, so you will lose the information very fast. So one of the paper will purify the silicon to 800 ppm. ppm means parts per million. Right. It means in 1 million atoms, sorry for the writing, you only have 800 that are silicon 29. So very high quality, very pure silicon. So that your electron won't see the spin easily, nuclear spin easily. That's the first thing. Second one, we need to have Zeeman splitting, right? So you do need to apply external magnetic field. It's pretty high, 1.4 Tesla. I will show you the paper later, right? So here, just give an example. I copied this from a paper. So this Zeeman splitting is going to split it into two levels under 1.4 Tesla. How much is that? We are going to do a calculation, okay? And you will realize that I need to put it in very low temperature because the splitting is still not enough. If you put it in room temperature, it will just ruin the quantum coherent state. And if you don't do echo, we talked about echo earlier, the T2 time is about 120 microseconds. Is this okay? Any concept that's unclear to you? Although this is a new material, we don't test it directly, but a lot of stuff can be tested in the midterm because we already learned what is Larmor frequency. So you should have all those equations. I can ask you to do calculation like this, right? But just now, I have a real example for you. Any questions about what is magnetic field, temperature, T2 stuff? Okay. Let's do a calculation, right? So we try to calculate the Zeeman splitting. So, okay, but now this example, okay, I do not, I should look at my cheat sheet. I actually have some more points to talk about here. Just want to provide you a few more equations. So this is Zeeman splitting, right? You should know this concept. And you should know that the Larmor frequency equals to EB0 divided by M, or gamma B0. You should know this equation, right? You should also know that, okay, the Hamiltonian is the magnetic moment times B in the product, right? And it splits into two levels. The first level is negative EB0 divided by 2m h bar, which is negative omega L. You know this already, so please study, right? H bar. And then here is another level, EB0 divided by 2m h bar equals to omega L to h bar. You know this, I don't need to say one more time, right? But the difference, right? They divided by 2, the difference is omega LH bar, which is correct, which is just the Zeeman splitting. One go negative by half, another go positive by half. We are just repeating the equation, right? Do you see that from rapid oscillation all to here? Okay. So let's do some calculation. And I think maybe one or two more slides, then we will stop. So for example, this is an example. Just calculation. For example, B equal to 10 Tesla. Okay, I add a 10 Tesla magnetic field. I put it in the dilution refrigerator at 10 millikelvin. Then I want to find what is the Zeeman splitting, right? So the delta E equals to H bar omega L. We already said that, right? You should know this already. This is omega H bar, right? Or this difference is H bar omega L. So how do we calculate it? It's equal to H bar times omega L. Omega L, I will go directly to G. Maybe, let me don't jump. Omega L is just equal to gamma times B0. This is something we learned before, right? If you don't use gamma, you don't use the gyromagnetic ratio, maybe you say, I prefer to use, since this is electron, right? But still, let's don't do electron yet. This is the gyromagnetic ratio, right? And then I would say, okay, I'm going to plug in the numbers. H bar is 6.626 times 10 to the power negative 34 divided by 2 pi. Right, this is H bar. What is G? For electron is about 2.002, right? And then charge is 1.6 times 10 to the power negative 19 divided by 2 times the mass. What is mass? If you probably don't know, 9.1 times 10 to the power negative 31. So I'm using SI unit, so this is kg, the mass of an electron. Yeah. And then times speed, which is 10 Tesla. I did not put the units, but because they are all SI, so it is okay. You go through the math, I get 1.856 times 10 to the power negative 22 joule. Right. But usually we want to put in EV, electron volt. Anyone know what is the meaning of electron volt? Energy of, say again.
Energy.
Very good. The energy an electron will gain when you cross 1 volt of potential difference. Yeah. So in EV, 1 EV definitely is equal to, because the energy it will gain is equal to Q times V, right? So I mean 1 electron, how to do that? I don't know. 1 E times, or let me just call it 1 E times 1 V, right? But you understand what I mean, right? But the charge of electron is 1.6 times 10 to the power negative 19 and times 1. So this is equal to 10 to the power negative 19 joule. Is that okay? The energy an electron will gain when you move from 0 across 1 volt of potential difference is 1.6 times 10 to the negative 19 joule, right? So that is 1 EV. So let's say you still don't get it, but not for exam, but now you really should understand, if I represent an EV, I will get rid of this annoying negative, large negative number, large negative exponents, right? So it will be, can you guess, right? Then it means what? 1 EV equals to this much of joule, right? So how do I convert to electron volt? I will just do this division. To get the EV, right? And this one will give me how much? Say again? Yeah, about 0.0011, yeah? And you go through the math, I mean, this is just equal to 1.159 MeV. MeV is minute electron volt. So that is the number we will always, the scale we are playing in in quantum computing, right? What is the thermal energy at room temperature? 26 milli eV. So you can see that, is it 26? Yeah, so it's like the room temperature energy is like 20 times larger than the energy separation of your qubit. If you try to operate your qubit, did I do anything wrong? Yeah, if you try to operate your qubit at room temperature, it won't work because the thermal energy is so large, or the uncertainty is so large, right? It's just like, as I mentioned earlier, you are standing, you are on a double deck bus, right? You can be on the first floor and upper floor. But when the road is vibrating like 104, 20 times or 24, you really cannot claim that you are on the first or second floor, right? Because it just have a big fluctuation, right? But luckily, we operate this in, this is 1, this is 2, kT over Q. You can plug in the number, but one way is that this is just equals to, this is the thermal energy. This just equal to, we're doing 10 millikelvin, right? I can just scale it because it is proportional to the thermal energy. So I know that room temperature is 26 MeV, so I divided by 300 Kelvin times 10 millikelvin. Right, so the thermal energy this is at 10 millikelvin, is equals to, you go through the math on my cheat sheet, you get 0.67 micro EV. Okay, So this one is what? Almost, why did I do something wrong? So the difference is pretty large, right? We don't need that large. This is how many times? Almost 1,000 times smaller. But I'm using an extreme case. This is 10 Tesla. In experiment, people use about 1 Tesla, so 100 times, right? And then here they use 50 millikelvin. I'm using 10 millikelvin, so 50 times. So 20 times, right? 100 divided by 5. So yeah, you need at least 10 times to 20 times of lower thermal energy to have a working qubit. And this can also ensure another criteria that you have a long decoherence time, long enough decoherence time, at least not limited by the thermal loss. Okay? So this is a hint. You are not expected to know everything, but you definitely should already know what is h bar omega, how to do the calculation, etc. So I will stop here, right? The rest we will discuss in the next class. With any questions, please let me know.